Okay, so in this problem we're asked to use integration to verify that the area of a circle of radius r actually is pi r squared. In other words, we want to derive the area formula for a circle, right? We've been told for a very long time that the area is pi r squared. But did you ever think to ask, why is it that? And who knows that it's pi r squared? We just kind of accept that it is. Well, now we can actually find it, compute it. Using calculus. In fact, integration with trig substitution. So let's check that out. So first of all, we want to take a circle of radius r. So it can be any circle, and since circles are preserved by shifting left, right, up, and down, we can actually simplify the problem to just looking at a circle that's centered at the origin. So that would be a circle of the form x squared plus y squared equals r squared. Right? Because if we shift it left or right or up or down, that's not going to change its area. Right? It's just going to change where it's at, not going to change its shape. So solving that for y, we would get y is plus or minus the square root of r squared minus x squared. Okay. So what I have here is I've gone ahead and graphed a circle that will basically take that shape, or basically take that form. I happen to graph x squared plus y squared equals 4. But basically I did that so we can see, hey, we have a circle here that's ranging from minus r to r. Yes, it's 2 in the picture. And so we want to introduce an integral. Now I could do the whole integral from minus r to r. Now I can't use the whole circle equation. I have to use half of it, the top half of it. But actually it's easier if I just look at 0 to r, because remember, integrating a definite integral when 0 is involved is often a lot easier. So what I'm going to do is I'm actually just going to look at this area here and then multiply that answer by 4. Okay, and if that happens to be pi r squared, when we're done, then awesome. So I just need to look at the integral here from 0 to r of the positive, the top half. Okay, and if I can show that that's equal to the right amount, and when I multiply by 4, I get pi r squared, then we have our answer. We have our answer. So, integral from 0 to r of my function, square root of r squared minus x squared dx. And so, of course, to do this, this is just straightforwardly an integral of the form a squared minus x squared. So we let x be a, or in this case, r sine of theta. Right? We have a squared minus x squared. So let x be a, which is r in this case, sine of theta. Dx would call for the derivative, which is just r cosine theta d theta. Okay, so we make those substitutions in. At this point, I'm going to leave off my limits of integration, and I'll bring them back later on. I don't want to convert my limits of integration over to theta right now. We could, but I'd rather not. So I'm just going to leave them off for now, rather than converting them over. And then later on, once we get back in terms of x, then I'll bring them back in and we can work out the definite integral part of it. So this will be square root of r squared minus r sine of theta squared, so r squared sine squared theta, times the derivative, which is r cosine of theta d theta. Okay. Right, and then we can factor out the r right? We can factor out the r there. Have the integral of the square root of r squared, 1 minus sine squared, times r cosine theta e theta. And we just keep going. So square root of r squared, r is the radius, so it's positive. So square root of r squared is just r. So when I group it with this other r here, right, then I'm going to have an r squared. So integral of r squared. And that's going to be square root of cosine squared times cosine theta d theta. But square root of cosine squared is cosine. And then I'm going to have cosine times cosine. So this all works out to be r squared integral cosine squared theta d theta. And at this point, we could use the identity, or we can just use our reduction formula. We have an integral of cosine squared. So remember our reduction formula. Says that the integral of cosine is cosine of 1 power lower, along with the sine, divided by that original power, plus n minus 1 over n cosine 2 powers lower. Okay, and so that's exactly what we're going to do, is use that formula. So this would be equal to r squared, okay, cosine 1 power lower, would be cosine theta sine theta. That's divided by 2. Cosine theta sine theta. That's divided by 2. And plus n minus 1 over n cosine of the 2 powers smaller. So n minus 1 is 1, so 2 minus 1 is 1, divided by 2. So that would be plus 1/2. And 2 powers lower would be cosine of the 0, so we're just down to d theta. Okay, so working this out, we'll have r squared on the outside times 1/2 cosine theta sine theta plus 1/2 theta. Normally we would have plus a constant, but since I'm eventually this is a definite integral, and as soon as I convert back to x, I'm going to be evaluating through my endpoints. I'm not going to bother with that step. Okay, so we've worked out the integral now in terms of theta. Now it's time to go back and find out what the answer is in terms of x. So let me just recap again. We were looking for the area of a circle of radius r. So we chose ones that were centered at the origin because, again, moving a circle out somewhere else doesn't change its area. So we set up the integral from 0 to r of the square root of r squared minus x squared. So to work that out, because we have an a squared minus x squared, we do the substitution, x equals a sine theta. Okay, we've carried through those substitution steps with both the x and the dx. Done a little bit of simplifying, and eventually we got to the integral of cosine squared theta d theta. Here we used our reduction formula, just doing a little bit of simplifying and rewriting. And now we're ready to convert over to theta. So to do that, we remember that x is equal, from theta to x. So we know that x is equal to r sine theta. X equals r sine theta. So we know that sine theta is equal to x over r. All right, so that's what we know. So we can easily substitute in for sine theta. That's going to be x over r. And we can easily substitute in for theta. Right? Theta is going to be the inverse sine or arc sine of x over r. What about the cosine? Well, to do the cosine, we need to complete the picture with the angle. We draw our reference triangle. So we draw our reference triangle with our angle theta in it. And we know that sine theta is x over r. So opposite side is x, adjacent or hypotenuse is r, and then we would solve for the third side, which should be r squared minus x squared inside the square root. And so now we're ready to compute the stuff that we need here. So in terms of x, our integral will be r squared times 1/2 times the cosine of theta. So cosine is the adjacent over the hypotenuse. So that'll be square root r squared minus x squared all over r times the sine of theta, which is just x over r, plus 1/2, and then theta, which is going to be, again, since sine of theta is x over r, theta is the arc or inverse sine of x over r. Okay. And then this thing now is all going to be evaluated between my two endpoints, which were 0 and r. Now here's what I want you to realize here when we start plugging these values in. This is going to be equal to r squared. So first we plug in r. And when I plug in r, I'm going to have square root of r squared minus r squared, which is 0. That's going to wipe out this whole piece here. Right? That whole piece is just going to wipe out. Okay? So we plug in r, and so we're doing arc sine of r over r, or arc sine of 1. Okay, what angle gives me a sine of 1? That's what arc sine of 1 is asking. What angle gives me a sine of 1? Well, that answer is pi over 2. Okay, and then we continue on minus. We plug 0 in. Well, for this piece, when I plug 0 in, for x, that's going to be 0 over r times all that other stuff, which is all going to become 0. So that piece is all just 0. And I do arc sine of 0. Arc sine of 0, well, what angle gives me a sine of 0? The answer is 0. So all those zeros get worked off, and we get that the area of that region is pi over 4 r squared. And then finally, the area of the circle is 4 times that. Because it was only a quarter of the circle. And so now we have proven, using calculus, that the area of a circle is pi r squared. Something you've been using for a long time, but probably never proved. Now with calculus, we can prove with certainty that the area of a circle is, in fact, pi r squared.